Good morning all. This is Dr. D. Khalandar Basha, working as Associate Professor in the Department of ECE, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today I am going to discuss the serial communication supported in 8051 microcontroller, which is UART, which stands for Universal Asynchronous Receiver Transmitter. The slides are prepared by referring the textbook, The 8051 Microcontroller by Kenneth Ayala. The serial communication in 8051, the data communication. The 8051 microcontroller is parallel device that transfer 8 bits of data simultaneously over 8 data lines to parallel I/O device. Parallel data transfer over a long distance is very expensive. Hence, a serial communication is widely used in long distance communication. In serial data communication, 8-bit data is converted to serial bits using a parallel to serial out shift register and then is transmitted over a single data line. The data byte is always transmitted with least significant bit first. Serial communication means to transfer data bit by bit serially at a time, whereas in parallel communication, the number of bits that can be transferred at a time depends upon the number of data lines available for communication. In the diagram, the first one is serial communication, where from the sender to receiver, or again reverse back from the sender to receiver, can be transmitted the data serially bit by bit. Only one bus will be present between the transmitter and receiver. Whereas in parallel communication, multiple lines are present for data transfer. How many bits you are transferring, that many number of parallel lines should exist between the transmitter block to receiver block. The two modes of serial communication are synchronous communication and asynchronous communication. In synchronous communication, the transfer of bulk data is in the frame structured at a time. Whereas in asynchronous communication, the transfer of byte data in the frame structure at a time. The arrival of the data at a fixed interval in serial communication, whereas in asynchronous communication, byte by byte we are going to be transmitted, which is padded with start bits and stop bits. 8051 has a built-in UART with RxD line, which is receive data for serial data receive pin, and TXT transmit data for serial data transmit pin on port 3.0 and port 3.1 respectively. In asynchronous serial communication, which is widely used for byte-oriented transmission, the frame structure in asynchronous communication is the data is appended with the start bit followed by the data and stop bits. The start bit, it is a bit which serial communication starts and it is always low. Data bit packet, the data bit packet can be 5 bits to 9 bits packet in 8051 serial communication. Normally, we use 8-bit data bit packet, which is always sent after the start bit. Stop bit. This is 1 or 2 bits. It is sent after the data bits packet to indicate the end of the frame. The stop bit is always the transmission rate, which we call as baud rate, the rate at which the data is transmitted is called baud or transfer rate. The baud rate is the reciprocal of the time to send one bit. The data transmission rate is measured in bits per second. In the binary system, it is also called a baud rate, the number of signal change per second. The standard baud rate supported are 1200, 2400, 4800, 19200, 38400, 57600, 1,15,200. In most of the communication, we are going to use the baud rate which is 9600. Normally, most of the time 9600 bps is used when speed is not a big issue. In asynchronous transmission, baud rate is not equal to the number of bits per second. This is because each byte is preceded by a start bit and followed by parity bit, optional, and stop bits. For example, in synchronous transmission, if the data is transmitted with a 9600 baud, it means that 9600 bits are transmitted in 1 second. For 1 bit of transmission, the time required we can calculate as 1 second divided by 9600, which will give us to 0.104 milliseconds. This is the time required for transmission of a single data in synchronous communication. In 8051, the serial communication have the TTL logic levels, which indicates for logic 1 and for logic 0, the voltage levels are defined based upon the TTL logic family. Over the years, the serial protocols have been crafted to meet particular needs of embedded system. Examples are USB protocol, Ethernet protocol, SPI, I2C, RS-232. In 8051, we have few SFRs supporting for serial communication. The 8051 supports a full duplex serial port, which indicates the data transmission and receiving the data will be takes place at the same instant. 3 special function registers support for serial communication. They are SBUF, SCON, and PCON. These are the 3 SFRs used for serial communication. SBUF register. The serial buffer SBUF register is an 8-bit register. It has separate SBUF register for data transmission and for data reception. For a byte of data to be transmitted via TXT line, first 8051 microcontroller will copy the data into SBUF. Through this SBUF, whatever the data is there, that will be transmitted on TXT line. Similarly, when the data is received on RXT line, first the data will be collected in SBUF. Then the processor will read the data which we are received on RXT line. SBUF holds the 8-bit data received by the RXT pin, received data pin, and read to accept the received data. The SBUF register, that is serial buffer register. This is the serial communication, a data register used to transmit or receive the data through it. The size of this SBUF register is 8 bits. The 8 bits are placed from B0, B1, B2, B3, B4 like this till B7, which is consist of 8-bit data. The next SFR corresponding to serial communication is SCON, which is serial control register. SCON register controls the data communication in 8051 microcontroller. It is used to set serial communication operation mode. This register contains mode select bits, serial port interrupt bit like TI, transmit interrupt, RI, receive interrupt, and also the ninth data bit of the transmission and receiving, that is TB8 and RB8. Also, it is used to control the transmission and receive operations. The SCON register, which is 8-bit size. The bit format of SCON register is shown in figure 4. The LSB bit is corresponding to RI, interrupt for receiving, TI, transmit interrupt. Ninth bit of receiving will be placed in RB8. Ninth bit to transmit will be stored in TB8. To enable the receiver, REN pin. SM0, SM1 for mode of operation. SM2 is for use a multi or coprocessor system. The SM0 and SM1 bits of SCON register will decide what is the serial mode of operation. If SM0, SM1 is equivalent to 0, the mode of operation is 0 and it is for 1/12 of the oscillator frequency, act as shift register mode with a fixed baud rate. If SM0, SM1 are configured as 01, the mode of operation is 1, which is a 8-bit UART with timer 1 determines the baud rate. 10 case for mode of operation, which is mode 2. The operation is, it will act as a 9-bit UART with a fixed baud rate of 1/32 of the clock frequency generated by oscillator. If you configure SM0, SM1 as 11, the mode of operation is 3, which is a 9-bit UART with timer 1 and determines the variable baud rate. Normally, mode 1 is used with 8-bit data bits for asynchronous communication, 1 start bit and 1 stop bit. The next bit, that is bit 5, which is corresponding to SM2, which is for multiprocessor communication. This bit enables a multiprocessor communication features in mode 2 and mode 3 of 8051 serial communication. The next bit is bit 4, which is REN, stands for receiver enable. If you configure this bit is equivalent to 1, it will enable the receiver. If you configure this bit is equivalent to 0, it will disable the receiving. The next bit, bit 3, which is TBI, which will hold the 9th bit of the transmitting data. The 8 bits are stored in SBUF and the 9th bit will be copied into TBI. After transmitting the SBUF data 8 bits, this TBI data will be transmitted as a last bit. This is the 9th bit which is used to transmit in mode 2 and mode 3 for 9-bit communication. The next bit is bit 2, which is RB8, which will give the 9th receive bit. When we are receiving the data size is 9 bits, 8 bits are received into the SBUF, 9th bit will be received in the RB8 position of SCON register. This is the 9th bit received in mode 2 and mode 3, that is 9-bit mode. Whereas in mode 1, if SM2 is equivalent to 0, then RB8 hold the stop bit that received for multi-core or multiprocessor system. Bit 1, which is TI, transmit interrupt flag. This bit indicates the transmission is completed and gets set after transmitting the byte from the buffer. Normally, the transmit interrupt flag is set by hardware at the end of the 8th bit in mode 0 and at the beginning of the stop bits in other mode. LSB bit, bit 0, which is for RI. RI stands for receive interrupt flag. This bit indicates reception is completed and gets set after receiving the complete byte in the S buffer. Normally, receive interrupt flag is set by the hardware in receiving mode at the end of the 8 bit in mode 0, and it will be occupied by the stop bit received time in other modes. Now we will see the various modes of operation for serial communication. The first one is mode 0, which is a fixed baud rate with 8 bit data transmission, act as a shift register. In this mode, serial port run in synchronous mode. The data is transmitted and received through TXD pin and RXD pin and is used for clock output. In this mode, the baud rate is 1/12 of the crystal oscillator clock frequency. In mode 0, the baud rate is always fixed, which is 1/12 of the oscillator frequency. Next, mode 1, which is a 8-bit UART with variable baud rate. In this mode, SBUF becomes a 10-bit full duplex transmitter. 8 bits are data, 1 start bit and 1 stop bit. The 10 bits are 1 start bit followed by 8 bit data followed by 1 stop bit. The interrupt flag, either it is for transmission or receiving, will be set once the transmission or reception is over. In this mode, the baud rate is variable and is determined by the timer 1 overflow. The baud rate we can calculate by 2 to the power of S mode divided by 32 into timer 1 overflow rate. S mode is the bit which is present in P count register, which will give 2 to the power of S mode bit divided by 32 into oscillator frequency divided by 12 multiply with, as it is 8 bit, the maximum count is equivalent to 256 for auto reload mode minus the count which you have placed in TH1 register, which is used for calculation of the baud rate in mode 1. Mode 2. In this mode, SBUF becomes 11 bits full duplex transmitter as well as receiver. The 11 bits are 1 start bit followed by 9 data bits and 1 stop bit. The interrupt flag for transmission TI for receiving RI will be set once the transmission and reception is over. In this mode, the baud rate is fixed and it is determined by the overflow of the timer 1 rate. The baud rate is given as it is equivalent to 2 to the power of S mode divided by 64 into the clock frequency of the oscillator. Mode 3, which is a 9-bit UART with variable baud rate. In this mode, SBUF become 11-bit full duplex transceiver. The 11 bits are 1 start bit followed by 9 data bits and 1 stop bit. The interrupt flag for transmission TI for receiving RI will be set once the transmission or reception is over. In this mode, the baud rate is variable and is determined by the timer 1 overflow. In mode 2, we are not having, it is fixed value. The baud rate is calculated for mode 3 as 2 to the power of S mode divided by 64 into timer 1 overflow rate, which will give us as 2 to the power of S mode divided by 32 into oscillator frequency divided by 12 into 256 minus the count loaded into TH1 register of the timer 1. The next one is P count register. Before that, we will see the power down and idle mode in 8051 microcontroller. The power down and idle mode features are used to save power in microcontrollers. 8051 has an inbuilt power saving feature that is useful in embedded application where power consumption is the main constraint. 8051 has two power saving modes, power down mode and idle mode. 8051 power control logic will be depends upon two control bits. They are ideal and PD, which are used for the ideal and power down mode respectively. These bits are present in P-count register. In power down mode, the oscillator clock provided by the system is off, that is CPU and peripherals clock remains inactive in this mode. In ideal mode, only the clock pulses are provided to the CPU gets deactivated, whereas to the peripherals clock will remains active in this mode. Hence, power save in power mode is more than idle mode. Now we will see how it will function. If power down is active, that means if PD is equivalent to 0, PD bar is equivalent to 0 because it is active low signal. So for active, we will write PD bar is equivalent to 0. When one input of AND gate is 0, the output of AND gate is equivalent to 0 and divided by 12 will also produce 0. So no clock pulses will be given for the peripherals like timer interrupt. The same 0 we are passing to the AND gate. As one input is 0, the output of this AND gate is also 0, so that no pulses will be generated for the CPU. Suppose if PD bit is equivalent to 1, if power down mode is not active, that indicates if PD bar is equivalent to 1, the output of AND gate is 1 ANDing with the oscillator frequency. Now we are going to get some signal with F oscillator, which will be divided by 12, that is F oscillator divided by 12. These clock pulses will be transmitted to the timer interrupt. Whereas these clock pulses will be given for CPU depending upon ideal pin. Suppose if ideal pin is active, that means ideal bar is equivalent to 0, the output of CPU is equivalent to 0. If you observe this case, when ideal mode is active, the clock pulses are not transmitted to CPU, whereas the same clock pulses are given for the peripherals. Suppose if ideal is inactive, that means ideal bar is equivalent to 1. Now the oscillator frequency, which is divided by 12, these clock pulses will be transmitted to the CPU also. F clock pulses divided by 12 clock pulses multiply 1 with will gives the oscillator frequency divided by 12 clock pulses. So when power down is not active, ideal is not active, the clock pulses will be received for the peripherals, for timers as well as for the CPU. If power down is active, that means PD bar is equivalent to 0, no pulses will be transmitted to the CPU as well as for the peripherals. If power down is inactive and ideal is active, in that case, the pulses will be transmitted to the timer interrupts, whereas these pulses will not be transmitted to CPU. So the CPU will be inactive state in the ideal mode, whereas in PD mode, the CPU as well as peripherals also will be in the inactive state. The next SFR is P-count register, which is power control register. P-count power control register is used to force the 8051 microcontroller into power save mode. The power control register of 8051 contain 2 power saving mode bits and 1 serial baud rate control bit, that is S mode bit. The P-count register is a 8-bit register, out of which the bit 4, bit 5, bit 6 are not having any significance. The MSB bit is S mode. B0, B1 are power saving mode bits. Bit 2, bit 3 are general purpose flags. Now we will see in detail. The MSB bit, that is bit 7, is S mode, which is for controlling the baud rate. If S mode bit is equivalent to 1, the baud rate is doubled in UART in mode 1, 2, 3, which are asynchronous communication. If S mode bit is equivalent to 0, the effect of baud rate with respect to S mode is inactive. That means whatever the fixed baud rate and variable baud rate is defined in the earlier expression, that will be executed. For doubling, we have to make S mode is equivalent to 1. The next bits are bit 3 and bit 2, which are GF1 and GF0, which are general purpose flags. These are general purpose flag bits used for users or for some applications. The next bit is bit 1, which is PD, power down. To enable the power down, we have to write this PD bit is equivalent to 1, which will enable the power down mode. If PD bit is equivalent to 0, disables the power down mode. So when you make the power down is enabled, the signal which you are passing for PD bar is equivalent to 0, which will make inactive clock pulses for CPU as well as for peripherals. If PD is equivalent to 0, that means PD bar is equivalent to 1. Then in this case, the clock pulses are given for peripherals as well as for the CPU. In this mode, the oscillator clock turned off and both CPU and peripherals clocks will be stopped. Hardware reset can cancel this mode. The LSB bit, bit 0, which is ideal, that is for ideal. If this bit is equivalent to 1, it will enable the ideal mode, and if this bit is equivalent to 0, it is disable the ideal mode. If ideal bit is 1, it indicates the ideal bar signal is equivalent to 0, which will inactive the clock pulses to CPU. Whereas for peripherals, the clock pulses will be transmitted. If ideal is equivalent to 0, then ideal bar will become 1, which makes the clock pulses for the CPU also. In this mode, the CPU clock turned off, whereas internal peripherals modules such as timers, serial port, interrupts work normally. Interrupt and hardware reset can cancel this mode. The steps to programming 8051 to transfer data serially. The T mode register is configured in mode 2, that is auto reload mode for 8-bit case, to set the baud rate. The TH1 is loaded with one of the value to set the baud rate for serial data transfer. The SCON register is configured indicating the mode of operation for serial communication through 8051. Next, run the timer 1, that is by setting the TRX bit to 1 to start the timer, that is timer 1 usually used. TI is cleared by the CLR clear instruction. The character byte to be transmitted is loaded into the SBUF register. Monitor the transmit interrupt flag bit by JNB TI, target location to see if the character being transmitted completely. To transfer the next character, go to the step 5. For mode 0 and mode 2, the baud rate is determined by means of 1 by 32, 1 by 64 of the crystal frequency as well as 1 by 12. Whereas for mode 1 and mode 3, it is determined by timer 1. For setting the baud rate, the value which we have to load into the TH1 register of timer 1 are shown in table 2. For 9600 baud rate, the value we have to load into the timer 1 TH register is FTH. For 4800 baud rate, we have to load the count into TH1 register is FAH. For 2400 baud rate, the value which we have to load into TH1 register of timer 1 is F4. For 1200 baud rate, we have to load the TH1 register of timer 1 with E8H. Thank you all. In the today's class, we have seen the data communication, the various types of data communications like serial communication, parallel communication, followed by synchronous communication, asynchronous communication, the data format for asynchronous communication, introduction to baud rate. Next, the serial communication supporting in 8051 microcontroller, the various SFRs corresponding to serial communication 8051 are SBUF, SCON and PCON register. Thank you all. See you in the next class.
Like, share and subscribe. hit the bell icon for more updates.